Solving the AC analysis, and this first example here we're going to do a base bias amplifier, and this is the same amplifier that we did the DC analysis on previously. There's a 390 k ohm resistor for the base resistor, the collector resistor 750, and a transistor with a beta of 300. Now in order to do the AC analysis, I've added in a signal here which is applied to the input of the amplifier with an input capacitor. And I've also added a load which I've attached with an output capacitor. The reason for these capacitors is to block the DC component but allow the AC component to go in. If you look at the signal level here, base bias amplifiers need a really small signal or you'll just saturate the transistor or turn it off. If you put 100 millivolts into this thing, if that adds on to the 0.7 volts that's already there, that would turn this transistor on completely. And if you subtracted 100 millivolts from the base voltage, that would make this 600 millivolts, which would turn the transistor off. So if you put any kind of a decent signal into a base bias amplifier, you're basically just going to jump back and forth between saturation and cutoff. So you'll see these circuits have very small input signals in around 10 millivolts. That means that this is pretty much 0 volts. If we attach that straight to the base, we've basically shorted the base to ground and it's no longer biased. So we need to use capacitors on the input and the output so that the AC signal can go in and get amplified and then filtered off the DC to create an output that is just an AC signal. The base bias amplifier, this is a common emitter amplifier because the emitter is taken to ground. You put in a positive sine wave here and you get a negative sine wave out. This amplifier inverts the signal by 180 degrees. If you remember from the DC analysis, we came up with a Q point that was about 8 volts and 13.31 milliamps of collector current. And the emitter current, this number here, is going to be used in the AC calculations. The DC emitter current was 13.35 milliamps. First thing we want to do is draw the AC equivalent circuit. And we do that, we talked about how to do superposition. If you want to know the impact of one voltage source, what you need to do is remove all of the other sources, which you do by shorting them to ground. And we're going to do the same thing here in order to draw an AC equivalent circuit, which is just the AC voltages and currents. So you start off by shorting out the DC supply. So the 18 volt supply here, we short that to ground. We still have an AC signal in and an AC voltage out, but if we short this to ground, we're going to pull out the effects of just the AC. When you've shorted that out, what you do is you transfer the parts over one by one from the schematic into the AC equivalent circuit. So for instance, this base resistor here, which when we short the DC to ground, it goes between ground and the base of the transistor. Over here, it goes from ground to the base of the transistor. The collector resistor would go from the collector to ground, and that's shown here. And then the load is connected to the collector through a capacitor to ground. So there's the RB, RC, and RL taken over. Now usually what I like to do is I like to leave a box for the transistor. I just kind of draw in a box and I write down base collector emitter. And when I'm ready to, I put the T model, or my appropriate model that I'm using to solve the problem, into the box. In this case, I put in a T model, which is a dependent current source and an impedance from the base emitter diode modeled by R'(E). Now the value of R'(E), that's the one thing that we need to take information from the DC biasing in order to figure out. And R'(E), it's an impedance, so it's a voltage over a current. And the current that we use is the DC emitter current. So that'd be 25 millivolts. That comes from Boltzmann's constant, divided by 13.35 milliamps. That gives me 1.87 ohms. And with that value, we now have values for all of the components on the AC equivalent circuit, and we can go ahead and start finding the important characteristics. First thing we do is we solve for Z in and Z out by Thevenizing. So in order to find Z in, what you want to do is stand here and look on the input of the transistor circuit and say to yourself, what is the impedance looking into the circuit? So if I look into the circuit here, I see 1, 2 resistances in parallel. I'm doing this by Thevenizing, so when I Thevenize, the current source becomes an open, so that's an open circuit. These resistors are not seen looking into the input of the transistor. So you would have that Zn would be Rb in parallel with R'E, but remember that R'E is an impedance seen on the emitter side of the transistor. In order to figure out its impedance looking into the base, we need to move it over to the base side, and we do that by multiplying it by beta plus 1. So here we are, Zn, it's Rb in parallel with R'E multiplied by beta plus 1, which is 390K in parallel with 301 times 1.87, which comes out to 563 ohms. Likewise, on the output of the circuit, to find that out, we stand here, we consider ourselves to be the load, and we look back into the circuit, we remove the current source, and we ask ourselves, what is the impedance looking that way to ground? There is only one resistor here, and that's the collector resistor, so Z out would be equal to RC, which is equal to 750 ohms. So now we've got Z in and Z out, and we can put those numbers into our 2-port model. And now we need to find the voltage gain, which is V out over V in. And the process for doing this is you start off by identifying the nodes or the piece of wires that represent V in and V out. So over here I've drawn this little orange line around this piece of wire here. This is all the input line. This is all the input voltage. It comes from the signal generator, it gets shorted by the capacitor, and it appears on this line. So this is V in, and if I look over here, this little green line I've tried to draw around this piece of wire, that entire piece of wire is V out. That is what's appearing across the load, so that's the output voltage. Now that we know where they are, we can write equations for V out and V in using transistor currents and impedances. So for example, on V out here, if I'm looking at the current going back and forth, this is the AC equivalent circuit. So the currents are all the changing stuff. So the current's going back and forth between the collector and the emitter. And when it comes out of the collector here, what the current comes out of here is IC. And if we're looking for no load voltage gain, so in no load voltage gain, what we want to do is remove the load and figure out the gain with the load removed. So basically the current that's coming out of the collector here has to go through this 750 ohm resistor RC. So V out has to be equal to IC times RC. And I've entered that into my equation here, my no load gain on the top side here. I have V out is equal to IC RC. And now I've got to find for V in. Likewise, the current's going back and forth here. This is collector current going out the collector. And then coming out here, this is the emitter current. So what goes through R'E is the emitter current. So V in is effectively IE times R'E. And I've got that down here on the bottom of the equation. So I've written the equations for V out and V in using transistor currents and impedances. Then you want to get everything in terms of IB using substitution. We know that IC is beta times IB, so we do that substitution. And IE is beta plus 1. It's a little bit bigger, so it's beta plus 1 times IB. So we go from IC-RC over IE-RE to beta IB times RC over beta plus 1 IB times RE. You can notice that we've got IB and IB in both the top and bottom. So we can cancel that out. We can cancel out the IB, leaving us with beta times RC over beta plus 1 times R'E. All of these values are known, so we can enter those values into the equation, and then we can solve for the final value of AV, which in this circuit is minus 399.2, or about minus 400. It is a negative gain. I didn't have any of that written down there, but this circuit has a negative gain. If I put in a positive sine wave, I get an inverted sine wave out of it. So that becomes, when this is 1 volt, this thing would be putting out minus 400 volts. Obviously it can't do that with 18, but it puts out a negative voltage because it's out of phase with what's coming in. So now we've got Z in, we've got Z out, and we've got AV. We need to draw the final AC voltage model, which is this down here. So this is the amplifier, and the amplifier is represented by an input impedance Z in, which is 563 ohms. We put that down in there. There's a dependent voltage source, and the voltage across these two terminals is AV times VN. So it's minus 399 times the voltage that appears on the input of the amplifier. And that gets delivered to the load through a non-zero finite Z out of 750 ohms. So using this, we can say, well, let's put a volt on the input of this amplifier and figure out what comes out. And I've kind of done that over here. Right? So this is the AV with the load attached. So the gain of this is minus 400. But as soon as I attach a load to it, I create an attenuator that reduces the output. So the gain with the load attached from V in to V out would be, now if I put a volt here, that would be 400 times bigger appearing across here, but then I'd have an attenuation of 10K over 10.75K. So I would get, if I put 1 volt here, I would get an output voltage of minus 371. So the gain with the load attached from V in to V out is minus 371. Next question might be, well, what if this is 1 volt and I have to set that up before I attach it? As soon as you attach it, you will get a voltage divider between here and here. So if you wanted to figure out the gain from VG to V out, well, what you would do with that, a little bit of an animation here. So the gain from V gen to V out would be, let's say this is 1 volt. First thing you would do is you'd have a voltage divider between the 563 and the 50 ohm. That's shown here. That would be the voltage that would appear in the input of the amplifier. That would get multiplied 400 times, so we would multiply it by 400. That's the voltage that would appear across the terminals of the dependent source. And then the voltage that appears across here would get voltage divided down to a slightly less voltage, which would appear on V out. So whatever the voltage is here, we need to multiply it by the voltage divider to find the final V out. So if I applied 1 volt here, I would get minus 341 volts here. So the gain from this point to this point is minus 341.